Section 3.3 is going to look at rate of change and then some behaviors of graphs. One way you may have seen rate of change before is in the slope. So the slope is your rise over run, or how fast the line goes up or down. So the way we find that is change in y over change in x. If you have 2 points, so essentially you take the y coordinates and subtract them. You take the x coordinates and subtract them, and then that's going to be your slope. When it's not linear, it's an average rate of change because it depends. It's average for whatever time frame you're talking about. So let's look at some examples. In 2007, the price of gasoline was $2.84. So that gives us a point of 2007, 284. Then in 2009, the price of gasoline was $2.41. So that gives us another point. Now, this probably didn't go up linearly. If you know anything about gas, it goes up one day, down the next, up one day, down the next. So we're just finding the average between those two dates. So if the y's are our money, we're going to subtract. And then on the bottom, we would subtract the years. So 241 minus 284 is going to be negative 0.43. And 2009 minus 2007 is 2. Then if we actually do that division, we get negative 0.215. So since it's money, we're going to say the average was 22 cents per year. That was the average rate of change at that point. If you're given a table, I don't know where that went. If you're given a table of a whole bunch of points, then what you're going to do is you're either going to select 2 if they tell you it's linear, or you're going to use the given information to do that. So you would just use whatever thing's there to get your 2 points and then use the slope formula. If you're given a graph with an interval, you're going to find the points at those 2x values. So at negative 4, we have 0. And at 0, we have, negative 4 goes up to 3. And then at 0, it also goes up to 3. So we would do our subtracting. 3 minus 3 over 0 minus negative 4 gives us 0 over 4, or 0. So here, the average rate of change is 0 because it didn't change at all. We see that it did, but we're just looking at that average. Another example, let's say we said negative 4 to 1. So negative 4 is still 3. 1 goes all the way up to 7. So then we would subtract. 7 minus 3 over 1 minus negative 4 gives us 4/5, or 0.8 if we had turned that into a decimal. Same idea if you're given an equation, you're just going to plug in those values to find the points and then subtract. So if I plug in 2 squared, f of 2 squared minus 1 over 2 would be 4 minus a half, or 3.5. So that's going to be one of our points, 2, 3.5. Then we plug in 4. So 4 squared is 16. Minus 1/4 is 15.75. So that's going to give us the other point. And then we do the same process. 15.75 minus 3.5 over 4 minus 2 gives us 12.25 over 2, or 6.125 as our average rate of change. So you have multiple ways to look at things. It's just a matter of what form it's given and what it asks you. For the behavior of equations or functions, we're going to look at increasing and decreasing, and then maximums and minimums. Increasing means it moves up, or the x value gets higher as you go to the right. Decreasing goes down as you go to the right. So the reason we give a direction is because I can stick an arrow here, and then you'd get a different answer if you're talking left or right. So we always go to the right. So this piece of the graph right here is increasing until it gets to this point, which is a maximum. That maximum is called an extreme value. It's the highest point in an area. Then we decrease until we get to the minimum, which is the lowest point in the area. And then we increase again. We can describe those with interval notation. So this part of the graph would have an arrow. So it would be increasing from negative infinity until that maximum, which is about negative 2.5. Then we decrease from negative 2.5 to this one, which the x value is 1.75. Then we increase again. So we're going to use the u, like we talked about in section 3.2. And then it's going to increase from 1.75 to infinity. So that's one way to show that increasing and decreasing. If we looked at this graph over here, we'd be increasing in these two sections, and we'd be decreasing in these two sections. And again, we're going to use our x values for these. So it's the x value of that max or minimum. So we increase from negative 3 to 0. And then again from 2 to infinity. And our decreasing are going to use the same numbers. We're going to decrease from negative infinity to negative 3. And then from 0 to 2. So if you notice, those numbers repeat because you go from one or the other. So when we talk about our extremes, we go back and forth between absolute and local. A local extreme is every single bump on a graph. So this is an extreme, this is an extreme, this is an extreme, this is an extreme, this is an extreme. Those are all local max and mins, anytime there's a bump. Absolute is when you're talking about the entire graph. So not every graph has absolute max and mins. If we look at this one again, we go up forever and down forever. So even though we have a local max at this bump and a local min at this bump, there's no absolute because it's going up forever and down forever. So you'll never get to a highest or a lowest point. If we look at this graph, it goes up forever on both sides. So there's not going to be an absolute max, but there is going to be an absolute min. So first, we have a local minimum. We have a local maximum. Then we have a local minimum. So every bump is a local. Now, if we look at this point, it's also the lowest of the entire graph. If we were doing our range here, that's where the graph would bottom out. Our range would be negative 3 to infinity, meaning that is an absolute minimum. So it can be both a local and an absolute because there's never a point lower than that on the whole graph. So that is what we needed out of section 3.3.